talking to Gaël Mourouga, PhD candidate at ETH Zürich, about flow batteries in this interview. So welcome to the interview, Gaël.
Thank you very much. I'm happy to be here.
Now, I'm really interested in flow batteries because the issue of utility scale storage is becoming more and more critical as utilities modernize their grids, as they increase the amount of intermittent renewables that they're integrating into their grids. And the question always comes up, what will we do for storage? So maybe let's start this interview with just an overview of what a flow battery is, please.
Sure. So flow batteries, as you may be aware of, were invented by NASA in the 1970s. And so at the time, they were building up on the work conducting during the Apollo project, and they were researching long duration storage. So I think the idea at the time was to have moon bases, which didn't really turn out to become reality. But then with the oil crisis in 1973, we realized, with the oil prices coming up, that maybe storing energy at a large scale would be a good idea. And that's when NASA really got more funding to research the idea further. And so at the time, they developed the iron chromium system. And then in the 1980s in Australia, the old vanadium system was invented at UNSW. And so this is where things really started, coming up for flow batteries, because the system really exhibited good performance. And so this is in the 1990s, we really saw scaling up of these systems, mostly in Australia, in China, also a bit in the US. And so, the main idea behind flow batteries is to store energy at the grid scale.
Right. So what are the general working principles of flow batteries?
Yeah, so that's an excellent question. So for example, in this phone here, I have, which should be a lithium-ion battery. And in this lithium-ion battery, you have kind of layered electrodes, right? In which we try to insert as many lithium-ion as possible. So in a flow battery, the general idea is that we're going to dissolve the ion, so lithium, for example, in a liquid phase. And we're going to use not a layered electrode, but really just a porous material. So imagine a kind of a carbon sponge. And the idea is to pump the electrolyte with the active molecules around the sponge. And so the liquid will react with the sponge and will give us some electrons, which then we can use. So there are a few consequences about this. So the main problem is that the energy density is very low, because our ions are dissolved in a liquid phase, right? So the energy density of the battery will be much, much lower than a lithium-ion battery. Now, the main advantage is that the whole electrochemical principle reaction is much more reversible. So in theory, you have a battery, so the electrolyte can last for 25 years. But then also we need to pump. So the efficiency of the battery goes down a little bit. So lithium-ion is typically going to be in the 90% range, 95%. Flow batteries will be in the 75, 80% range due to the pumping. And so they're really more suited for grid-scale storage than portable applications.
Right. So if I understand this correctly, because I've seen photos of flow batteries and they basically look like big sea containers, big metal boxes. And so inside you've got the electrolyte, the liquid electrolyte, and this sponge that you're talking about. So you're circulating the electrolyte around the sponge. Whereas in a typical lithium-ion battery, you've got an anode and a cathode, and you've got your electrolyte and some separators, and it works. So it's a very different kind of construction. And you have to have a lot more battery, a bigger size, to do the work that to provide the kind of storage that is required. Have I got that more or less correct?
Yeah, that's absolutely correct. I think you really painted a good picture of the system. But one of the consequences about this is that these tanks of electrolyte that you mentioned, that's our energy component, and then this porous electrode that's in the middle, that's our power component. And so the main consequence is that power and energy are scalable independently. So let's say you want to add 2 hours of storage to your system, well, you can add a tank, which is something that you cannot do with a lithium-ion battery.
Now, what kind of chemistries are the most commonly used these days?
So vanadium is by far the most common and the most performant to date. So the biggest projects are, in the megawatt hour scale in China, in Australia. But I think on the old continent and also in the US, there are some new technologies emerging. The one I'm working on is aqueous organic. So the idea here is not to use any metal in the active material. So to use kind of, polymer molecules dissolved in water. That's the main idea there. And that could solve, some supply chain issues with respect to metal supply.
Okay, so aqueous, so we're talking about water and polymers. Are we talking like a type of plastic?
We're talking really more like a salt, an organic salt. So yeah, imagine kind of a material that's made of carbon, oxygen, and nitrogen, kind of a big molecule, which is dissolved in water.
And where would that molecule come from? How would you create that molecule?
Yeah, that's a good question. And actually, one of the molecules we're using was designed in the 1970s as a herbicide. So there's a whole synthesis process behind it. And what you end up with is kind of this blue liquid, which has been used a lot in Southeast Asia as a herbicide. And yeah, I think it's pretty cool in a way to use a herbicide in a battery.
Well, we'll get to you a little more detail on your research in just a moment. Let's talk about flow batteries in the context of grid scale storage. Mm-hmm. How do flow batteries tick some of the boxes that lithium ion does not?
So as I mentioned previously, I think there's the duration of storage. So with a flow battery, you can design a system that will store 8 hours, 10 hours, 12 hours of peak power. With a lithium ion, typically you're limited to 4 hours of storage. And so in markets where you want to be doing intraday trading, maybe peak shaving on the electric grid, I think then flow batteries become interesting.
Now, I interviewed a company a couple of months ago that has an iron flow battery. And mm-hmm. they claim that battery can do 12 hours duration now. With some tweaks over the next few years, they'll get up to 16 hours. And they say that that's about all that's required. Basically, if you're doing, let's say your power is generated by solar, then if you have 16 hours of sunlight and you're generating solar power, then you charge up the battery and you only need it for, X number of hours while the sun isn't shining. Is that kind of where we're at? I mean, it sounded to me like these were relatively inexpensive. They provided enough storage for the grid. And it really then was a question of scaling up the application, scaling up the installation of these things on the grid so that you had enough of them. Have I got that? Have I got that more or less correct?
Yeah, absolutely. Just by curiosity, was the company ESS Inc?
Yes, it was.
Okay. Excellent. Yeah, I've heard of them. Yeah, I think their iron flow technology looks really promising because iron is quite cheap if you compare it to metals like cobalt, lithium, vanadium. And yeah, I think you got it right. What we need now is scaling up. Also for aqueous organic chemistries, we have pretty, I would say, interesting demonstrators at the 100 kilowatt hour scale. And so now at least in Europe, we're really looking into scaling up and having this first industrial scale system, which we can install in the grid.
What about European startups? There seems to be a lot of activity in this space.
Also in the US, but I have to confess that I'm more familiar with European startups since I've collaborating with a couple of them. So in terms of aqueous organic chemistries, I think the leading one currently is Jena Batteries in Germany, in Jena, Eastern Germany. They're also the one with whom I collaborated the most during my PhD. Then in France, you have Chemiwatt, who are developing a chemistry that was actually invented by Stanford University, if I'm not mistaken. And then in Italy, you have Green Energy Storage, also kind of a similar system, quinone-based system. And then I know that there are some things going on in the US also from the ACCURE group at Stanford. I'm a bit less familiar with what they're doing, but it's looking really promising also over there.
Now, where are these startups at in their development? Because we hear about the process of you go from the bench to maybe a pilot to a demonstration to commercialization, and there are always problems with access to capital in there. The valley of death, where the technology is promising enough that it looks like it could be scaled up, but at the same time, the capital isn't available to do that, and promising tech startups fail. So where are we at with these startups?
So I think, here I have to be careful not to give, any protected information or anything. But I think what I can say is that 2022 is going to be a make it or break it year for these kind of startups. Because on the demonstrator scale, on microgrids, it's working. And now these startups are going to have their first contracts coming up with the first customers. At the large scale, we're talking a few hundred kilowatt hours, perhaps megawatt hour. And they have to deliver. And they have to deliver this year and in the 5 coming years. And
well, you mentioned microgrids, and there's a increasing interest in microgrids because, and one of the motivations for that, of course, is resiliency. And we, especially in the U.S., we've seen failures in California and in Texas, and so a lot of communities are saying, well, why don't we build our own microgrid and that we can control and we can build resiliency into it? What are the applications of the flow battery technology for microgrids?
So that's actually a very good question, and I think we need to go back to the general picture between centralized grid and microgrids. So as you mentioned, microgrids, the main advantage is that they offer built-in resiliency, right? Because suddenly you don't have to regulate the frequency on a national grid. You just have to regulate the supply and demand of electricity over the scale of a town, a village, maybe. So that's for sure, that's interesting. But then you have to wonder in Europe and in the US, we have already built this very well functioning national grids, right? So do we need to change all the system to go toward microgrids? But then I think there's a market that's interesting. It's Africa and Southeast Asia, where these centralized grids haven't been built yet. And so what would be the best applications for them? I think they will be looking for the cheapest batteries. In terms of both investment cost and also levelized cost, on the whole lifetime of the battery. And so in this regard, flow batteries, they're a bit more expensive on the investment cost, but then since they offer longer lifetime, typically, then you can have the levelized cost go down. So now the question is, how competitive can flow batteries be against lithium ion with respect to the investment cost of the battery?
Well, let's talk about that. I do a lot of interviews with battery experts, and we talk about, the price per kilowatt hour of a cell or price per kilowatt hour of a battery of the pack. And I think, at Bloomberg NEF, the last time I interviewed them, they were saying that last year, the average price across the EV industry was $132 per kilowatt hour for a pack, but the price per cell was down under 100 already, and now they're forecasting very dramatic drop in cost for lithium ion. We might see by the early 2030s $40 a kilowatt hour for battery packs. So given that that's kind of the context for, at least on the EV side of lithium ion, can you tell us a little bit about the costs of flow batteries?
Yeah, again, very good question. And I think the thing we have to realize about cost questions is that the main driver between the reductions in cost is what we call the learning curve effect, right? So the more you install capacity and the more you learn and the more your costs go down. And so I think there's a general good correlation when you plot it on a log scale, is that for each megawatt hour that you install, every time you multiply the installed capacity by 1,000, you divide the cost by 10. And lithium ion, I've been going down this learning curve for 20 years now. And flow batteries, and especially these, innovative chemistries, as you mentioned, iron flow or aqueous organic, we're just at the beginning of this learning curve. And so the question now is, where can we be in 5 to 10 years from now? And I think this also, we go back to the make it or break it year. If we make it, and if more contracts keep coming for these chemistries, I think we can have the same learning curve as lithium ion.
Now, lithium ion, as well as other renewable technologies like wind and solar, have benefited a great deal from government support. And it's either they've been directly subsidized or they've been supported in other ways by policy and regulatory regimes. And it seems to me that given the importance of storage to utilities, and in climate policy, electrification of economies is a big policy directive. So are governments coming to the table and saying, okay, look, we've got this great storage technology now, flow batteries, but it needs to scale up. That'll bring the cost down. We're going to put some money into it to support that process, like we did with wind and solar. Is that where we're at?
That's a good question. That's a very good question. And I think, well, as a European, I'm going to go back to the events that are happening right now in Europe, especially Eastern Europe, because the main question we're facing now is the governments are facing is that we may be going towards a rarefication of Russian gas. And so that poses the question, what are the alternatives? And what kind of subsidies do we need to invent in order to, fill the gap left by Russian gas? And this, I'm afraid, I'm not qualified enough to answer. But I think there's definitely something to be done by the European Union and the US on this front. So subsidizing long duration storage technologies.
Yeah, that would seem to make a lot of sense, because it was only last month the European Union released its plan to get off Russian gas entirely. And a lot of it had to do with electrifying things like home heating with heat pumps and electrifying transfer. And so if you're going to produce all that power, you're going to need more storage. It would just seem like, so I guess we'll watch what happens in the European Union as they proceed with this strategy. So let's finish up the interview, Gaël, with a discussion of new technology. So we've talked about iron flow a little bit. You described some of the work you're doing on aqueous
organic.
Organic. What other kinds of technologies are emerging in the flow battery space?
That's a good question. So recently, I did some data scraping on an energy-related forum on Reddit, and I just plotted, the kind of. So on this forum, there are articles, news articles that are being posted, and people can upvote or downvote a bit like, likes on Facebook. And so I plotted the total score of the articles and the number of comments that were below them in order to see a bit the storage technologies that were the most discussed. And so from then, what I could see is that the most discussed technology in the news right now is hydrogen. So for grid scale storage, a lot of people are talking about green hydrogen, this kind of hydrogen economy. So I have my doubts on this, but maybe this would be, this would warrant another podcast entirely. But hydrogen is definitely the one that is gaining the more steam right now, let's say. Then right after hydrogen were flow batteries. So I was pleasantly surprised to see that a lot of people are discussing flow batteries. And then there were a lot of other technologies. So gravity storage technologies like pumped hydro, which is by far the most common technology installed on the grids right now, which is facing some limitations in terms of geography. So typically you need a higher reservoir and a lower reservoir. So you usually build this in mountainous regions. And we've kind of reached the limit of what we can build right now, at least in Europe. Then there's thermal storage, which looks really interesting. But here the idea is to use this concentrated solar power plants and concentrate the solar power and melt some salt. So it's called molten salt technology. This looks also very promising. But if we're looking at applications that are meant to stabilize the electric grid, then it's not really for this application. It's more about concentrating the power from the sun. And then there's a wealth of new battery technologies, sodium ion, liquid metal batteries, sodium sulfur batteries, and also all the metal air batteries, so zinc air, iron air. And all of these look very promising. I think some of them can have different niche applications, obviously, but yeah, the one that seems to be emerging the fastest right now seems to be flow batteries.
Is it fair to say, Gaël, that that we're developing a whole plethora of storage technologies? Some of them are batteries and some of them are hydrogen and compressed air and pump storage and all of these. And over the next, 5 to 10 years in particular, as we start to really electrify and modernize grids and so on, that these utilities are going to have their pick of the best technologies. As you say, niche applications. What do I need? I'm a utility in Western Canada that has, hydro, or I'm a utility down in Midwestern US that has, this particular mix. Maybe I've got renewables and some coal that I'm trying to get off and some gas, those sorts of things. But then they'll have all the technologies they need. It's a matter of picking the right ones, integrating it into their grid, learning, that learning curve you're talking about. Costs are coming down. I suspect that 10 years from now, you and I will look back on this conversation and be quite surprised at how much progress has been made on utility scale storage.
Yeah, I think you're absolutely right in saying that there's many different applications and many different use cases and many different, contexts, national context. And I don't think it's possible to have one size fits all technology. So far, we had lithium ion, which was, it's a really great technology. You can use it in, phones, cars, stationary storage. But yeah, in the future, I think different niche applications or different countries will need different technologies. And there is definitely room in this market for a lot of, emerging technologies.
Well, Gaël, thank you very much. Really appreciate this.
Thank you very much.